Our current understanding of the universe falls under the categories of quantum mechanics and classical theory. Classical mechanics lifted off in the 17th century with the development of Newton's laws of motion, and while the behaviors of large objects can be explained by these laws, when attempting to describe smaller objects, classical mechanics begins to break down. Quantum mechanics is a successful theory at a huge range of energy levels. Our current understanding of elementary particles based on quantum mechanics is a model known as the Standard Model. Under classical mechanics, there is the assumption that all aspects, such as momentum and position of a physical entity, could be precisely measured simultaneously, but these notions fall apart at the quantum level. Classical mechanics was unable to explain certain properties of light, such as black body radiation. Here, we introduce quantum mechanics to explain this phenomenon. In 1905, Albert Einstein proposed that light is emitted as quanta, meaning that light is made up of energy-carrying photon particles. Later, in 1924, Louis Victor de Broglie introduced the concept in which quantum objects have properties characteristic of both waves and particles, an idea that now is known as the wave-particle duality paradox. In classical mechanics, this idea is not present. Another main contrast between classical and quantum physics is the occurrence of entanglement. Entangled particles are connected in such a way that measurements collected of one particle correlates to the measurements of a second particle, regardless of whether or not they interact. It is also well known that the correlation is observed even for particles that are so far away that a signal at the speed of light would be too slow to transmit the information about the correlation. Thus, these correlations propagate at superluminal speed. While wave and particle effects are experimental facts, is a particle an extended object, such as a wave, or a point-like object, or both? It is not clear. If the particle was both extended and point-like, we would have a paradox, as it would be something never seen in our macroscopic world. How could a physical object be both large and small? This is called the particle-wave duality paradox. One of the complications in the microscopic world is the fact that when a particle is observed, its state changes in such a way that things can only be determined probabilistically, making this phenomenon of particle and wave difficult to directly measure. Many interpretations have been developed in an attempt to explain quantum effects, such as the Copenhagen interpretation.
The Copenhagen interpretation stands as the standard interpretation of quantum mechanics. It was largely devised by Niels Bohr in the 1920s, unsurprisingly in Copenhagen. At the heart of the Copenhagen interpretation lies the interpretation of the principle of complementarity. The measurement of one complementarity quantity will destroy information of the other complementarity quantity. The principle of complementarity can be seen in how the Copenhagen interpretation explains the wave-particle duality paradox. A quantum object becomes a wave or a particle depending on the observation. The wave and particle are a complementarity pair, meaning that an electron can be observed sometimes as a wave and sometimes as a particle, but never both. When an experiment is conducted to measure the wave-like properties of an electron, information about the particle properties are destroyed. An electron is neither a wave nor a particle, without any context or measurement. At observation, an electron or any other quantum object becomes either a wave or a particle. The Copenhagen interpretation is built upon probability. Schrödinger's wave function assigns a value, the amplitude, to each possible experimental outcome. The probability is the square of the amplitude. This means that the wave function is the complete description of a quantum object as it encompasses all the possible states that it can have. When an observation or a measurement is made, the wave function collapses into one state. The quantum object being described becomes physically real. It is important to note that this collapse does not obey Schrödinger's equation since it is instantaneous. Since waves are a measure of probability, it becomes impossible to determine what a particle will do. Determinism breaks down, which means the universe has no defined future. The probabilistic nature of the Copenhagen interpretation has profound consequences and can be seen in Heisenberg's uncertainty principle. If the wave function collapses to give the momentum of a given particle, then it becomes impossible to determine the position of that particle. Knowledge of the momentum's value would make it impossible to obtain knowledge of the position of a quantum object. Because of the principle of complementarity, it is impossible to know everything about a given quantum system. First postulated by Louis de Broglie in 1927, the pilot wave theory is another interpretation of quantum mechanics, and it vastly differs from the Copenhagen interpretation. The pilot wave interpretation outright ignores the wave-particle duality paradox, as de Broglie considers the waves in the quantum system to be physical, rather than probabilistic. Since Einstein proposed the particle nature of light, which was thought to be a wave at the time, de Broglie reasoned that particles would also have a wave nature. This physical wave is not a probabilistic wave, as the Copenhagen interpretation would say. Instead, the wave of a particle acts as a guide or a path for the particle to follow. This means that the past is defined by values and variables already defined, and the future is already determined. Therefore, the pilot wave theory is a deterministic theory. If all of the particle's properties were known, then there would be an accurate prediction of where the particle will ultimately land. However, there are issues as due to the uncertainty principle, it is impossible to know both the momentum and position of a given particle. Instances like this give rise to hidden variables. In order for pilot wave theory to work, hidden variables are required. These variables are properties of a particle that cannot be measured. The values of these variables determine the path of the particle. A major problem with the pilot wave theory is that the equations that determine the path of the particle does not always allow fulfillment of these conservation laws. If we take the conservation laws as a fact of nature, this theory comes short of describing physical reality.
Before we dive into the Glassboro interpretation, we need to take a look at quantum waves. Quantum waves are oscillations that freely propagate in the vacuum. Sometimes quantum waves might be thought of as states of the vacuum, as in the case of the hydrogen atom. Surrounding the proton, there are vacuum states ready to be occupied by an electron. In this case, the vacuum state or quantum wave is a sort of standing wave with different shapes for different energy and angular momentum levels. When a particle occupies one of these standing waves, the square of the absolute value of the wave represents the probability for the particle to be found at that location. It is important to realize that in the Glassboro interpretation, particles, real or virtual, are point-like objects at all times. Real particles are stable particles that fulfill the energy-momentum relation. Virtual particles do not fulfill the energy-momentum relation. They last for a short time before they are absorbed. Real and virtual particles carry particle properties such as energy momentum, angular momentum, charge, color, etc. Since particles carry energy momentum, they transmit forces. Unlike the Copenhagen interpretation, the wave function does not undergo a collapse in this model, which preserves the idea of a unified reality. Instead of a collapsing wave function, the Glassboro interpretation introduces a peculiar interaction among particles and with quantum waves. When a particle occupies a particular quantum wave, there is a unique connection that is created between them. This same connection is broken when the particle vacates this state. Interestingly enough, experiments that deal with quantum entanglement have shown that this connection between the wave and the particle is instantaneously created or destroyed. The Glassboro interpretation treats the vacuum as a physical object, which is able to support all quantum waves at all times. Quantum field theory reveals that quantum waves of every frequency and wavelength are all simultaneously present in the vacuum at all times. This idea is supported by experiments such as the Casimir effect. Similar to the pilot wave interpretation, the Glassboro interpretation models quantum waves as physical objects which are able to influence the path of the particle because of their connection with them. The Glassboro interpretation differs from the pilot wave theory in that the quantum waves themselves cannot do the pushing and pulling on particles. In the Glassboro interpretation, virtual particles transmit energy and momentum from sources to particles. Therefore, virtual particles do the pushing and pulling on real particles. The job of quantum waves is to direct this exchange of energy and momentum according to the values the quantum wave has. Another major difference with the pilot wave is that the Glassboro interpretation requires that the conservation laws are fulfilled at all times. Fulfilling the conservation laws requires that a free particle may not obey some of its quantum wave's directives. For instance, if the free particle is connected to a quantum wave packet which contains many components with different energy and momentum, the free particles will only obey the directives of the one quantum wave component that is related to its actual energy momentum. The free particle would ignore the other quantum wave's components. In this way, the particle's motion would be consistent with the conservation laws. If the free particle approaches an external source of virtual particles, such as another particle or the nucleus of an atom, then it might obey other components of its full quantum wave. The external source would make it possible for the particle to change energy or momentum.
Finally, we notice that quantum waves are deterministic since they obey wave equations.
Particle dynamics is also deterministic with respect to the conservation laws. However, it is not possible to precisely measure position and momentum of a particle. Thus, it is not possible to know the precise energy, momentum, and angular momentum. We have to settle for the description of the dynamics of the particle in terms of quantum waves. The description of the dynamics in terms of quantum waves is necessarily probabilistic.